All right, today's lesson is going to be running a probability situation. This is our scenario. A special promotion for its 20-ounce bottles of soda. A soft drink company printed a message on the inside of each bottle cap. Some of the caps said, "Please try again," while others said, "You're a winner." The company advertised the promotion with the slogan, "1 in 6 wins a prize." The prize is a free 20-ounce bottle of soda, which comes out of the store owner's profits. 7 friends each buy one 20-ounce bottle at a local convenience store. The store clerk is surprised when 3 of them win a prize. The store owner is concerned about losing money from giving away too many free sodas. She wonders if this group of friends is just lucky or if the company's 1 in 6 claim is inaccurate. Create and perform a simulation to model this scenario. All right, as an overview, when it comes to simulations, you are expected to be able to deal with them using tactiles, meaning some hands-on manipulatives, technology, for us, meaning a random number generator on our graphing calculator, and random number tables. Okay, the first thing we're going to focus on today is tactiles. Now, we're dealing with a situation with a 1 in 6 chance of winning a prize. So the tactile that this should be screaming at us is the standard 6-sided die. When you have one roll of the die, the probability of any one single number is 1 out of 6, which is what we're testing here. So that's what we're going to use for first part of this activity. So in terms of writing it up, first thing we're going to have to do is to state specifically what the numbers are going to stand for. Now, we can choose any one particular number to represent the winner and the rest to represent the loser. For simplicity's sake, it would be better to choose 1 or 6, the beginning or the end, of which one's going to be the winner. I chose to make 6 be a winner. What we're going to do is roll 7 dice. The rolling of the 7 dice will model the 7 people going into the store to buy sodas. We're always going to have to be specific in terms of what we're recording and what we're going to display. We're going to have some kind of table or graph at the end of this that we're going to be basing our conclusions off of. What are we recording in that table? We're recording the number of 6s, or in other words, how many people are winners. Sometimes when you do these simulations, there are specific instructions as to how many trials you should be doing. For the purposes of a write-up, if they don't specify it, you're just going to use the generic many, many times. Okay, then what are we doing after we get this data? We're going to use the compiled results to determine the experimental probability of having at least 3 winners among a group of 7 people who purchased a soda. You want to be specific in stating that we're determining the experimental probability. We're not basing this off of a formula or a rule. We're basing this off of an actual experiment, which may or may not be the same result as if we use some kind of formula or set number of rules. All right, we're going to need some type of graph or table or something to record our results. So they gave us a sample one at the bottom of this particular page. So what we're going to do is just use a number line. I'm going to scale it 0 through 7. That represents no winners, 1 winner, 2 winners, 3 winners, etc., out of 7. And what are we recording? The number of 6s, which represent the number of winners out of the group of 7. So let me just get that onto a separate page for visualization purposes. 0, 1, 2, 3, 4, 5, 6, 7. Number of 6s, which represent your winners. Your axes needs to be scaled. Axes needs to have a label. So I have the 7 dice. I'm going to roll them. Oops, that wasn't a very good roll. They landed on top of each other. There we go. So in this first trial, we have 1-6, which means we have one winner out of the group of 7. So we mark a 1. Second trial, got one winner again. Third trial, can't see that. Let me back that out a little bit. No winners. Mark that. Next trial, no winners again. 2 winners. Now it turns out for this particular simulation, you need somewhere in a range of about 50 trials in order to get decent data. Now, based on what we know in Chapter 5, we don't really have a good knowledge of, well, 50 is what it takes. That's going to be a topic that we're going to learn a little bit later in the year. What kind of sample size or how many trials do we need in order to get the types of results that we're looking for. But for now, not your decision to make based on things you don't necessarily know at this particular point. We need to do this about 50 times. All right, for the sake of time in this video, I am not going to roll this dice 50 times. I'm going to use the data from a previous year. So, I already have the data put into the graphing calculator. And L1, that represents all possibilities, no winners, 1 winner, all the way up to and including 7 winners out of a group of 7. We did 50 trials in this particular class. So of the 50 trials, 14 of them had no winners, 22 had 1 winner, 9 had 2 winners, etc. That's the information that's in L2. And then in L3, I have the relative frequency. So 14 of the 50 trials, or 28% of them, had no winners, etc., etc. So I also constructed a graph, which we're going to compare to a different graph in a moment. All right, back to the first page. The conclusion that we're going to want to write should look like this. Based on our simulation, the experimental probability of. That's how we need to begin this, because we're not basing this off a formula. We're not basing this off of a fact. We're basing it off of something we actually did, an experiment that was run. Okay, specifically, what are we testing? At least 3 winners in a group of 7. Okay, with these types of simulations, we're usually not interested in an exactly 3. We're interested in results that are at least as extreme as 3. So at least as extreme as 3 would be 3, 4, 5, 6, 7. Because if you have more than 3 winners, then that even builds the case more for the store owner who's thinking that maybe it's a lie, that maybe the 1 and 6 isn't true, that they're giving away too many sodas. Unless you got a nice, clean, even decimal here based on your experiment, you always want to have the about or the approximately, if that's a rounded number, and then some kind of concluding back to what's going on here. Should the store owner be concerned or not? And if they are concerned, why? If not concerned, then why? Some kind of concluding sentence there. So back to the data from a class of mine from a year or 2 ago. What would the conclusion look like? Based on this simulation, the experimental probability of having at least 3 winners in a group of 7 is 10%. At least 3 winners would be the sum of all these numbers here. 0.08, 0.02, and then 0, 0, 0. So 0.08 plus 0.02 is 0.10. So the experimental probability of having at least 3 winners is 10%. All right, the cutoff value that we're typically going to use for problems like this is 5%. If there's a probability of less than 5% of something occurring, it's considered to be an unusual event. In this case, it would be evidence that maybe the store clerk is correct and that the people were lying about the 1 and 6. But since the 10% is not less than the 5%, The store owner should not be concerned because the probability is not less than 5%. And I think I already stated everything that's here. Let me just read it through to be sure. Having a probability of less than 5% is typically considered to be an unusual event, and is typically the cutoff value in situations like this where you're looking for statistical evidence to test the claim we're concerned. So there are times where you're specifically told what that value is. That's going to be known as their alpha value when we get a little bit later in the class. If you're not given a specific alpha value to use, we automatically default to the 5%. That's the typical one that we would be using. All right. Now, based on what we know in Chapter 5, we don't have a way to calculate these probabilities theoretically. Turns out in Chapter 6, we are going to learn some stuff that would allow us to do this. But based on our knowledge right now, our only way to test this claim is by running a simulation. Well, how does our simulation compare to what would happen, or what the theoretical probability of what would happen is? So one quick thing is to compare the graphs. Okay, overall general shape. The data, when graphed for our experiment here, looks roughly like that. Looks roughly like that. So just in terms of overall shape, the experimental data lined up pretty well to theoretical data. All right, let's take a look at the number tables. So theoretically, there should be about 28% of the time that there are no winners, 28%. Theoretically, about 39% versus 44%. 23 versus 18, so two decimal places, 8 versus 8, 1.5 versus 2. So our experimental data came pretty close to the theoretical data. And with 50 trials, we kind of expected that to occur. All right. The theoretical probability of having at least 3 winners in a group of 7 is 0.0958. So that would be the summing of all those numbers right there. That's the probability of at least 3. Well, we got, in this experiment, 0.10. So 0.10 versus 0.0958, pretty close. Based on our Chapter 5 knowledge of probability, we're unable to calculate this without relying on a simulation. In Chapter 6, we will be learning methods that will allow us to solve this type of problem theoretically. I already addressed that prior to that reading. All right, Chapter 5 concept that we talked about, law of large numbers. The law of large numbers says that if we observe more and more repetitions of a chance process, the proportion of times that a specific outcome occurs approaches a single value. The simulation example on this page is based off of 50 trials. If we were to increase the number of trials by the law of large numbers, our experimental probability of 10% would come closer and closer to the theoretical probability of about 9.58%. So paraphrasing this a little bit, if we did 500 trials instead of 50, then that would come closer to that. If we did 5,000, 5 million, 500 million, the more trials that you do, the closer the experimental probability comes to the theoretical probability. All right, let's go back and address other ways this simulation could have been done. So, what if we were to do this using a random number generator? We would still need to specifically state what our numbers are going to represent, same as here and here. But instead of rolling dice to get our data, we're going to be using a random number generator. We want to generate 7 whole numbers from 1 through 6, repeaters allowed, and record a number of 6s. All right, whenever you are dealing with random number tables or random number generators, you have to be specific in terms of what's happening with repeaters. When we did a simulation earlier in the year, or simulations, I don't remember how many we've done, that involve like sampling people for surveys or testing, you don't sample the same person twice. So it didn't make sense to consider the repeaters. Here, 2 winners in a group of 7, well, it's expected. So the repeaters are allowed. And then the bottom part here, that's going to be the same. Repeating it many times and then making your conclusion. So where'd my calculator go? So in terms of the actual keystrokes, math, prob, and we have 2 random numbers, 2 random number options that we've looked at. Random int, no repeat. Okay, we want random int. We want repeaters to be possible. So that's what I'm choosing. Looks like I already have this set up. Lower bound 1, upper bound 6. That's the range of numbers we're choosing from. 7, how many of them are we choosing? And then paste. So, in this first trial of 7 random numbers, we have no winners. Second enter, no winners. Second enter, 3 winners. Second enter, 1 winner. Second enter, 2 winners. So we would fill in all the information in a table or graph, something similar to what they gave us here. Then we would calculate that experimental probability and make our conclusion. Again, in the interest of time, I'm not going to do the button pushing 50 times on a graphing calculator, but that's how it would play out. All right, next, what if we were to do this using random number tables? Remember, with random number tables, sometimes you need to block your digits. Like if we were using dice that had more than 10 sides, like a Dungeons and Dragons type of dice, then we'd have to block it from 0, 1 through whatever. But since we're dealing with single digit numbers, we can just do the 1 through 5. So the first 2 lines, what stands for what, that's the same as it was above. It had the potential to be different if we had to block our digits. Okay, your book tends to use this line, this statement right here, starting at line 101 of Table D. Okay, Table D just happens to be what your textbook calls the random digit table. Other textbooks will give it a different name. You can get random number tables off of different websites that made them call them differently, but your book refers to it as Table D. You don't necessarily have to start at line 101. Some random digit tables don't even have 101 as the first line. So start at a random line of a random digit table would be a fine replacement sentence for that. Okay, then we have to look at, what are we examining? We're examining groups of 7 digits. You have to be specific in terms of how many are going to be in each group. 0, 7, 8, 9 don't have any meaning in the context of this problem, so those are going to get skipped. We are allowing repeats, and then the rest in terms of what we're recording and what we're doing would be the same. So just to begin the process of what it would look like for the first couple trials. What I'm going to do is first cross out what we're going to be skipping. So we're skipping 0, 7, 8, 9. So I was just looking at the first line going across. I already crossed out the ones we're going to be skipping. So the first group of 7 digits would be 1, 2, 3, 4, 5, 6, 7. So right there we have our first group of 7 digits, no winners. 1, 2, 3, 4, 5, 6, 7. Here's our second group of 7 digits. We got 2 winners. 1, 2, 3, 4, 5, 6, 7. There's our third trial, no winners, and go through. Okay, one thing that I did forget to emphasize that I glossed over that's different, where is that here? Oh, when you're working off of random number tables, you want this specific statement right here about at each trial, where do you pick up where you left off? Or where are you going to go? In this case, or in all cases, unless we're told otherwise, we're going to assume you just continue where you left off in the random number table. Some rubrics require that you state that. Some rubrics do not. It's safer to have it there than not. The point of the matter is they don't want you to go back to where you started and then do the same trial again, where you're going to end up getting the same numbers. All right, quick run through in terms of what you're responsible for on the actual AP exam. You're not going to be required to run a simulation that uses tactiles. They're not going to give you dice during the test for you to do something with. They don't technically require a graphing calculator with a random number generator in order to take the test. People that don't have a TI-84 or similar technology are going to have a tough time with many of the questions on the test, but it's not actually required. So in these two scenarios, you would be expected to be able to design a simulation without necessarily carrying it through. They could describe one to you and ask you to critique it. They could describe it to you with results and ask you to interpret the results. Those are all very fair game, very strong possibilities of questions that you could be given on the AP exam. Okay, with random number tables, it is possible that they could ask you to actually do a simulation with random number tables, because they could give you a table already embedded within the test. Now, I've seen questions in the past where you had to design it and run it. I've seen questions in the past where they already designed it for you. You just had to run it on the tables, and then the same as the above, it's possible that they give you the results of it, and then you have to critique it or interpret them. Lately, the random number table questions seem to be becoming de-emphasized. They're not as common as they used to be. If you're going to play what's most likely to be on the test, it would probably be one of these two versions of asking the questions without actually running the simulation. And I think that wraps that up for this video. Yes, it does.